computer scientists, all kinds of things. So I'm here today to talk to you about what I call arity science. So if you're curious about the developments, what we're doing, you can go to this very easy to remember site, arity.science. And it's a multidisciplinary project. It's not just pure mathematics, but today I'm here to talk to you about the pure math side and the more computational side. So I want to open with a question for the audience. I'd like to probe what you think is the most impactful piece of technology or framework, invention in the history of mathematics. Shout some examples to me.
Blackboard.
Yes. I love that you gave me the right answer.
May take a second.
Yeah. So I completely agree. So this worked wonderfully, my little experiment, because I was going to justify that yes, the Blackboard, or effectively, written form, is probably the most important technological advancement in the history of mathematics. And today I'm going to try and convince you that we might be in the sort of rungs of the next step, and we're not quite there yet. And I want to contribute my little suggestions or possible developments there. So I am going to hop on the diagrammatic hype train, because I mean there's a few people here who are on the diagrammatic hype train, but more specifically I want to hop on the hypergraph train. And yes, I want to tell you very briefly about these things in case you haven't heard of them before. So conceptually, a hypergraph is basically a collection of data structures on a set of elements. And data structures here is a bit flexible. You can think of data structure as you wish. Maybe more directly, and suggested by the name, is a higher-arity generalization of graphs. So essentially something that looks roughly like this, right? So you can have not just pairwise connections between nodes, but you can have multi-adic connections between nodes. But most importantly, you can have different typed edges. It's not just a subset. So typically in some areas of mathematics, in combinatorics specifically, hypergraphs are usually thought of as just subsets of the power set of that, which is a little bit simplistic for our purposes. So a bit more formal definition, you have nodes, which is just a set of primitive elements. You have edges, which is technically a multi-set of discrete data structures on nodes. Again, formalization of these structures might be a bit flexible to the user's liking. And importantly for us, labeling, which is just a map from nodes to a set of symbols in the usual way. So data structures could be formalized, for example, in the theory of combinatorial species, if you know that. Otherwise, you could think of different ways to implement, like we do ourselves. So we work in with a Mathematica implementation of hypergraphs, and that's what we've been working on in the last year or so. And so for us, nodes are unique ID symbols. Edges are a pair of bits of data. One is what we call a bond, which effectively is just a set of such unique ID symbols, and a spine, which effectively is just a directed graph of such ID symbols. And then labeling in Mathematica, these are just annotations, as you can imagine, it's easy to track. So a hypergraph effectively looks conceptually something like this. So it generalizes graphs in two ways, as I mentioned before. You have higher-arity connections, but you also have multiple arity connections. So you, in particular, have unary edges that can be just on a node, or you have ternary and higher. And importantly as well, you have heterogeneous data structures. So, for example, this could be like a bag that just has no order. This could be a cycle. So the idea of edges being a bond and a spine can be visualized a bit like this. So if you pay attention, for example, to the cycle here, which is a ternary edge that has some inverted cyclic symmetry. We want to first say that there is a bag of nodes that define the edge, and then inside you have a directed graph that essentially gives you this cyclic symmetry. So for example, this other pairwise undirected edge might have this complete directed graph inside to represent that there is no symmetry. So similarly, if you wanted a directed edge, you might have a spine that is just one directed edge. Okay, so as I say, we are developing a Mathematica paclet, a couple of colleagues and I, at the Wolfram Institute, and so I want to show you basically how this looks and works. So the basic idea, if anyone is familiar with the graph object in Mathematica, is to extend the graph object into the hypergraph object. So how this works is, syntax is very similar. You provide a list of edges primitively. You could also declare the list of nodes if you want. And this object here, I mean, this is a graphical representation of the hypergraph above. This is already computable. It's typically in Mathematica. You can take this and visualize the actual structure over there. So there are several options. As I said, the types for the edges and the labels, this are just annotations on your edges. There's different ways you can plot this for more a blackboard feel. And so we have a few functionality. We have a few functions implemented already that gives us general, useful functionality to do the basic things with these objects. So construction of hypergraphs is really quite simple. You can just give a list that essentially is your edge list, and then you can wrap it with hypergraph, and that basically constructs the hypergraph. But of course we can do, and you can generate random ones and so on, but we can do a bit more sophisticated stuff by constraining by connectedness, constraining by simplicity, and so on. We have this feature that is currently a little bit experimental, but it should work, which allows us to actually define hypergraphs manually. So I don't know if this is going to crash because Windows is a little bit unstable, but I can, yeah, it didn't behave. Oh no, it did, okay. So you can basically implement your hypergraph like this. You can have other things, you can move things around, etc. And then you can basically, this thing is going to have a lot of style annotation, but basically the data structure is over here. You have your hypergraph. And so we are adamant about the visual interface and so on for ease of access. Right, so importantly, we also have sort of good enumeration functions that allows us to control, for example, simplicity. These are simple hypergraphs that you can control the number of nodes. You can control the number of, so this is basically a signature that tells you 2 unary edges. This tells you 2 binary edges, right? So it's amount of edges, arity in that signature. And so basically these are all the 3-node hypergraphs with that signature. And you can play around with simplicity, you can play around with connectedness. If you say all true or false, that means when you expect. There are these enumerations, and just to connect with my presentation Tuesday, you can generate all the ternary hypergraphs with 3 edges, simple and connected by default. And then you might recognize many of the diagrams that I was using the other day. So these are the 9 possible hypergraphs that exist like that. Anyway, and yeah, there's some taxonomy here that we can look at things like labeled simplicity, which is when your hypergraphs are labeled with unique labels, because they might be non-simple in the conventional sense, but maybe simple when you consider the labels. So anyway, I wanted to have this more as a reference if there are questions later on, but I'll continue with my presentation. So the other point I want to make is that in my project, my research project, I've been relearning category theory. I did learn it a bit when I was doing my PhD in Edinburgh, but I have been relearning it. And so I wanted to stress a particular conceptual approach to category theory, or so-called diagrammatic approach. So to do that, let's first go back to kindergarten and try to walk you through a very elementary set of steps. So imagine that you're in kindergarten and you're learning to count for the first time. You're given this kind of thing. You have to count this set of objects. And you're a clever kid and you say, yeah, I can identify 1, 2. There's another group there that looks more complicated. But those 2 seem close enough. That's, again, I counted 2, so I can count 2 again. So I have those. And this looks like, 2, 3 times, right? So it's not too complicated. So maybe you advance a little bit in maybe primary school and you learn a little bit of arithmetic. And you express that the total count of this is going to be by this very complicated expression. It's a symbolic expression that will be arcane when you're 6 or something. And so you're really going through your basic arithmetic and you're told that you should manipulate that according to the rules of arithmetic, and you learn them. So you're scratching your head and say, well, actually, but what do I do first? Where do I apply this rule? So just basically, you're learning, you just scan, say, well, 1 plus 2, I know what that is. So that's one option, first option. Then you apply that. Okay, 2 times 3, that, really go ask your mother or something. Like, what is it? Okay, 6. So I know how to do that, and put it there. And I have 2 branches, and I can have to work with both of the branches. So there I have to figure out, actually, I know how to do that. So I also know how to do 1 plus 2, and I get implicit with both. And again, maybe now you ask your mother something again, and it's like, yeah, that's 9. So I completed the calculation. So this is a completely trivial thing to do in front of this audience, but I want to emphasize that, in my opinion, this somewhat encapsulates mathematical practice to a great degree. And I mean, many people might disagree that there's very important prerequisite steps, but to me, this really fundamentally captures at least one of the fundamental aspects of what doing mathematics is. So I want to look at composition of morphisms first from this very conceptual presentation as an example, and I want you to think of it as a rewriting rule. So that means that the sort of input box is thought of as a pattern matching entry, and the output box is essentially an output after a rewrite. So something that is going to match locally in a diagram, and then it's going to maybe delete those or keep them, depending on your perspective, but importantly add a new edge that has some memory of where it came from. So imagine that we want to test this rewriting perspective on basically the simplest diagram that you could think of in a category which is basically concatenating 3 morphisms, which, if you think about it, is basically the next smallest diagram of the rule for your pattern matching. So the point I want to make here is that I can see the basic axiom of associativity, that is, the first 2 lines of a category theory book, as a property of a rewriting system. So this may be completely elementary for most of you, but I'm trying to make a point, bear with me. So I'll go through the same gymnastics. I have my initial state, and you're like, oh, where can I apply my pattern? So ABC is definitely a pattern, so I can apply it there. And so I rewrite that part to that composition, but I can also apply it to BCD, so I apply it to that composition. And now I have 2 independent diagrams that, again, can be applied, that have a match for the rule, and both give a diagram that has a morphism between A and D. So the reason why I draw this, I mean, technically these are 2 differently labeled diagrams, so they're not confluent in the strict sense, but of course we all know that if we want to impose associativity, that's how you identify those two arrows or 2 morphisms. So the point here is that you can essentially equate associativity with the literal confluence of this diagram, of this rewriting system, which you're thinking of the diagrams, in this case, as labeled graphs or labeled multigraphs. So this to me, when I was studying this higher-arity algebras, I was very inspired by this elementary fact when I was sort of relearning category theory. I realized that actually many of the algebras that I wanted, in fact, all of the algebras that I was interested in and I knew could be recovered in this way. So I won't show you all of them because it's just an exposition of the same thing over and over, but I'll give you a tour of what I call the principle of diagrammatic simplicity. So diagrammatic simplicity refers to the simplicity of the hypergraph representing the diagram. So a simple hypergraph, remember, is one that has no loops and no multi-edges. So actually, it is labeled simplicity here, just for sure. I'll call it diagrammatic simplicity. So these are all the examples that I've kind of compiled. There are more, but maybe these are the most illustrative of all of them. So just for reality check, let me show you our composition, which is what we just did. And maybe I'll increase the font size a little. So this is the implementation of the thing I just showed you, but in our paclet, in Mathematica. So maybe don't worry too much about the specific syntax. This is just what we are working with, but I can show you what it means all the time. And again, the position of labels is not very efficient right now. But I hope you can see clearly that this is composition of morphisms in a category, right? You have X and Y, and this remembers the labels this way, and we have this dangling node, which is important because it's the intermediary node. And so every time that we're going to pattern match, we'll match with this side. So I'm going to do the same thing. I'll take this as a diagram, so FGH, so a chain of 3 morphisms. So if you're missing the labels, by the way, the system takes the name of the name of the node as the default label. So just to make it less cluttered. So what we call tuple associativity, just to be very specific, that is for this particular data structure, can be seen as I just illustrated with hand-drawn diagrams as the confluence property of this rewrite system, so a very simple rewrite system. So of course, this is non-confluent, strictly speaking, because the two labels are different. But if we take what I call the skeletal diagrams, which is basically removing all the labels, you get this kind of rewrite system, in which case it is confluent. Right? This sort of gives you a hint, I have a confluent skeletal diagram, and therefore I should be thinking of some axiom imposed. So actually, our paclet is specializing in analyzing the causal properties of these systems. So we can see, for example, the events, or the rewrite events, and how they relate with each other to analyze essentially what is the dependence of these rewrites. And so what actually characterizes this particular system is that it's not only that it's confluent, that's not so exciting in some sense when you have reductive rules in these finite diagrams, but the fact that it is so with a superposition of rule applications. What I mean by this is that the patterns, when they are applied, as you can see here, the 2-3 application has an overlap with the 2-3-4, sorry, the 1-2-3 application has an overlap with the 2-3-4 application, right? Namely, the morphism in the middle is seen in both rule applications. So you can say, why is that relevant? Well, so by the way, this is how we can see that explicitly. This is what the Wolfram Institute called the branchial graph. Basically, shows you which events are connected by this overlapping. So basically, the causally dependent events of your rewrites. So I just want to point out that these are causally dependent events that happen when you get associativity. And bear this with you because this might be relevant in other examples. So I have a lot of examples here. Is anyone particularly curious to see some of them? I have two that I definitely want to show because they illustrate aspects. Yes?
I'm sorry, I'm not sure I understand.
Mm-hmm.
I mean, we use diagrams, and the diagrams have no information about the order of operation, because the knowledge of the operation is associated, and so the order is irrelevant. So it seems to me that you are making some kind of simplistic argument.
No. So thanks for the question, because that's actually an interesting aspect of this. So this is pure hypergraph rewriting. I'm not assuming anything about it. That's why I started with hypergraphs, and I'll just show you this is how we're going to rewrite them purely, right? So the fact that the arguments are ordered, so that's actually why I have the line composition example, is that the topology of your directed graph diagram here actually allows you to identify the diagram as a tuple, right? Because the internal sort of dependency of the connectivity tells you actually your morphisms are captured by a tuple of morphisms. But for example, if you had this, what I call line composition, which is basically undirected graph rewriting instead of directed graph rewriting, then you no longer have that property, and now your composition is characterized by a bag or a set. A multi-set of morphisms. And the same argument applies, and what you get is bag associativity, right? Instead of tuple associativity, you get bag associativity. Now the rewrite system is a bit bigger because you indeed have all the sort of possible permutations in this particular notation. But again, the argument applies the same. The bare diagram is confluent. You have this system now, and then you should equate all this all these diagrams, because they are all diagrams between 1 and 4. So they would be sort of 6, or I don't know how many. I think it's more. It's 9. Sorry. That's 4, 8. So there's 8 possible expressions there. They should all be equated. And they correspond to the idea that if you have a commutative and associative operation in the usual parallel, you can swap the order of both the brackets and the elements inside the brackets. So yeah, it's a good question, but no, we're not assuming that. We're not doing that kind of circular thing where we are assuming kind of associativity in the background. And that's kind of the key. I mean, I should have stressed that our goal was to abstract what associativity was in the particular theories that we knew it, and try to capture it with some very parsimonious notion, that's what I'm trying to call this principle of diagrammatic simplicity, which is this yoga of, you generate the diagram, you see if it's confluence with no labels, and then you observe the label expression, and then you get some term equations from that. So unless there are some suggestions for this, I will show you something that looks quite different. So for example, a dagger. This might be very, very simple, but a dagger is simply the rewrite rule that takes a directed edge and reverses the order of the directed edge. And remember, you always keep some kind of information of where you came from in terms of naming, so that you can trace. Technically, you always label by the entire diagram that came before, but that's a different point. So first, involutivity. We exercise the principle of diagrammatic simplicity by saying we begin with our diagram F from R to S in this case, and we apply dagger. That's an arrow from S to R now, so there's no multiplicity yet. But if we apply it again, we get an arrow again from R to S. So that's a multiplicity because now we had an arrow F, and now we have an arrow F dagger dagger. So the principle of diagrammatic simplicity asserts that those two should be the same, right? And that's involutivity. Similarly for anti-homomorphism property. Now, if you combine this rule with the composition rule, which is another feature of this approach, that your rules are not just one, because one is applied in all possible ways. You can have as many as you like, and they all apply equally. So if you have that, and you begin with two morphisms, F and G, or two arrows, so I should say, these are not in category, which is in diagrams, and with two arrows, you can go on the way of doing composition on this side. You can go on the way of doing daggers on this side. And then eventually you're going to find composition first and then arrow here, and at some point you will find like there a dagger, composition, dagger. So those two are going to be diagrams that are tagged the same between 1 and 3, but they have different names, so same principle. Right? So yeah.
How does this, doesn't this compare like to just enumerating all well-typed equations and inserting them basically?
So the point is, that you don't want to think of equations at all, right? That's kind of the point.
Well, you're generating equations, right? You're generating, in this case, you've generated the equation that F G dagger is G dagger F dagger.
Yes, but you generated it if you're looking for it. So my point is that this system recovers equational statements if you want to, right? Like, I'm not saying that this is the way to generate them, or it's a particularly clever or efficient way to generate them. Is that if you don't know what equation should be, but you know how to implement an algebra in this way, you might actually do away with thinking in terms of equations, and you might just look at this sort of causal dependence. Right,
but in terms of like how this procedure is unfolding, it's like you're enumerating term sequences,
yes,
which are well typed.
yes,
Like that satisfy the domain or the source and target of these arrows and so on.
Yeah.
And then whenever you find two such expressions that have the same type, then you say maybe it would be a good idea to say that they're equal.
Yeah. That's what this is doing. Yes, that's correct. But the point is to move away from that sort of typed expression approach and just keep with the causal properties of a rewrite system approach. Just for reasons that will be clear in a moment. And as I said, these names are convenient encapsulations of the diagrams, but technically the names are the full diagrams that came before as a label. And that's where things get more complicated when you go into higher, because this is the ordinary unary and binary stuff that everyone knows, but when you go into higher-arity, this becomes much trickier. So anyway, I'll show that there. We also have an action, so it's not only operations on a set, but also sort of maybe like a semi-group action or a monoid action or a group action, something like that. To do that, you consider now edges of different arities. So you have a binary and a unary, and you basically define the action as, and this is not very well rendered here, but basically the directed edge is pulling the unary edge from the node to the target node, the source node to target node. So when you consider this together with composition, so action composition and arrow composition on this sort of minimal diagram, same idea applies, right? You can first compose and then apply the action, or you first apply the action and then compose. So you get two different expressions and you get this typical sort of associativity of actions sort of property. So anyway, so I could go on. There are many examples that all fit this pattern. So importantly, there's high order stuff. So we can do, for example, operand composition and sort of operand associativity. This is in fact a list of such rules, because obviously you have operands of different sizes and you want to characterize all the sizes. But if you want to look at, 2-to-1 operand and 3-to-1 operand and how they compose, and this rendering is not particularly neat, I'll be better in a tree position, but effectively this is what happens. So you can play the same game, draw the diagram, and you will get associativity of operand composition there. So the discovery that was made thanks to this approach was that we knew semi-heap associativity, also expressed in this way, which is almost ternary associativity, except that you're flipping D and B in this middle term here. Otherwise, it will be literal associativity. And the rediscovery of these algebras was by considering one of the diagrams one of the ternary hypergraphs that we enumerated, that was a ternary hypergraph of 3 edges that allows us to basically rewrite the system and consider this long, what we call it the fish for obvious reasons. We call this the long fish for obvious reasons. And then you rewrite this system with that rule, and you end up with these grid states in the end. And you can see that here the bracket is correctly written. So again, with the same idea, then you remove all the labels, you think of the diagram as confluent, so you do the same argument. So this was quite encouraging for us. But then we got into the really interesting one, this Bhattacharya-Mesner composition. There is a ternary operation that is not really well understood. And we started to think about possible initial diagrams that might give us confluent properties. And we did find one, and there are many, but we found one that was promising. And we said, oh yes, we remove all the labels and we do get a confluent diagram, beautifully like this. But unfortunately, what this amounts to is computation order independence. So basically, the fact that, sorry, it's loading some graphics below. So basically, it means that you have an operation that has ABC first argument in a bracket, CDE in a bracket, and so on. So you have 3 operations inside a ternary operations, and basically this is the order in which you take them. Right? You contract one, you take one operation, you contract the other one, you take another operation, and so on. And so you have a confluent system, meaning there's a single output of your operation, but it's not giving you any algebraic data. The connection with what I said earlier, that is more than just confluence, is that here there is no overlap. So there's no real causal dependence between these rewrites. So if you think about diagram, the rewrite rule is this, where you take 3 triangles into this single triangle. So you can see that this bigger diagram is basically 3 such triangles put together. So that looks like kind of a tetrahedron without a face. So you think of this, you take a tetrahedron and you plug 3 tetrahedra in each of the faces. That's the diagram. So obviously rewriting that by collapsing tetrahedra into the missing face is an independent process. They don't interact with each other. So interestingly, you do get a confluent system, but you don't get a confluent system that has algebraic information. It doesn't impose any axioms. So the punchline here, and I get back to my talk, is that we can do hypergraph-based computation to, in particular, search for these higher-arity operations. So there's a few advantages of this. First is that it's cognitively close to informal mathematical practice. We're really trying to get as close as possible to just writing things and the computer knowing what to do. It is fully computable, so it has direct interface with other formal systems. These are just more or less standard hypergraph encodings. We have a formula for generalized theorem proving just by looking at the causal properties of abstract rewrite systems, which might be more efficient for some things, might be less for others, but at least it's a different approach, or at least a different flavor. And most importantly for me, it bridges formal, informal, and experimental mathematics. By experimental here, I mean that there's a bunch of mathematics that have existed since computers have been around that basically creates species of things that exist in your chips or in your machines, and we can study them almost like natural science, with them being fully computable and formal. So, brief vision of the future. I began my talk by saying, what do you think is the most impactful invention in the history of mathematics? And you correctly pointed out to be Blackboard. So I want to be thinking that we collectively, and particularly in our project, are developing something like the Blackboard 2.0, where we want to sort of take all the best features of the Blackboard, but infuse it with all the properties of the computer processes that we have today. So something like hand-to diagram programmable graphical calculus would be sort of a slogan to try to aim for. Exploit 2D and 3D environments, and to develop computer-assisted mathematical intuition, not just mathematical computing or mathematical processes, but intuition. So just to give you a glimpse of this, so on our side, we have, as I showed you already, this is stacked. Okay, so we have a way to input hypergraphs already graphically, where you just click around and you draw. We also have the same thing for rules, so it's really easy to come up with, oh, I want to see if this particular diagram recovers this algebra that I know of. So it's quite easy to do that. You can come here, I hope this one collapse. So, for example, if you wanted to do the usual thing, you can take this diagram. By the way, you can label it by left-clicking here. So, for example, I can say this is F. So it means, actually, I want to give it a string name. And, oops. I might make it order. Yeah. I'm not sure. Right. So this is how you would draw, for example, morphism composition. So conveniently, if you click this arrow, the diagram is just copied here, so it's easy to just edit here. So I just want to delete this, and click here, and click here, and E, and it remembers the last name you entered, but you can change it to whatever you want. So you can do F, G, and yeah. So when you actually run this object here is already a rule, and it's going to apply to diagrams, and the labels are going to be used as pattern matching. So that's already sort of given. So the idea, of course, is to have some kind of graphical interface that users could very quickly draw their diagrams and implement the rules as they are learning. And so it is that the system would compute maybe behind the scenes all the rewrite systems and maybe highlight some or some. And just to give you an idea of what kind of stuff we're thinking about as mostly educational, is to have this 3D rendering of graphs. So this is, I can explore, I can drag things are labeled, I can highlight some like balls or regions. This will be, this is an old one, but it could be sort of a hyper-edge with that higher-arity there. Let's see, let's show some things and some colors, and you can run the rule, in real time here, or you can do some steps manually, explore it, and so on. So these are the kinds of environments we're thinking. Mostly, again, this 3D render for promotion and visualization and educational purposes. But yeah, that's basically the idea here. So yeah.